Hey everyone, welcome to another science news segment. Today we're going to talk about a couple science news stories that have to do with stuff in outer space. And as you know, this is one of my favorite subjects in all biology, so I'm pretty excited about it, and there's some pretty cool stuff in here. So let's get into it. So our first study is about the discovery of the largest molecule ever found in a planet-forming disk. Okay, so a bit of background information first. We know that organic molecules are really abundant in outer space. Vast clouds of organic molecules have been identified in both interstellar and intergalactic space, being ejected from geysers on moons and composing dust clouds orbiting young stars or planets. And spectroscopic analyses of these clouds have provided valuable insight on their chemical composition, including a range of small organic molecules, usually with up to 6 carbon atoms. And we believe that a lot of these small organic chemicals may act as precursors for the chemical building blocks of life. They're the building blocks of the building blocks, in other words, like amino and nucleic acids and sugars. So for example, some of these clouds in outer space contain molecules like methanol, formaldehyde, hydrogen cyanide and isocyanide, and ethyl formate, among some 200 or so other chemicals that are known to science. All of these molecules that we found so far have been pretty small, with either 6 or fewer carbon atoms. Or actually, not just carbon atoms, but they typically possess no more than 6 atoms total, including hydrogen atoms. So my correction there, and that makes for some very small atoms. Because keep in mind that water, H2O, 3 atoms right there. So some of the biggest atoms that we've seen in space, the biggest molecules we've seen in space are barely more than twice the size of a water molecule. So these are pretty small. But now a new discovery, which is the subject that we're going to get into here, involves the identification of the largest ever organic molecule found in space to date. This molecule is dimethyl ether, which possesses 9 atoms. It has the formula CH3OCH3. Now this chemical was found in the planetary disk in orbit around the star IRS-48, which it's about 444 light years away from Earth in the Ophiuchus constellation. Okay, so let's get into this press release from the European Space Organization. I believe that's what the ESO is. The European Southern Observatory. My bad. There we go. Okay, well, let's get into this. Using the Atacama Large Millimeter Submillimeter Array in Chile, researchers at Leiden Observatory in the Netherlands have, for the first time, detected dimethyl ether in a planet-forming disk. With 9 atoms, this is the largest molecule identified in such a disk to date. It is also a precursor of larger organic molecules that can lead to the emergence of life. Okay, so here it looks like we have a quote from Nishanti Brunkin, lead author of the study that was published in Astronomy and Astrophysics. Brunkin said, quote, "From these results, we can learn more about the origin of life on our planet, and therefore get a better idea of the potential for life in other planetary systems. It is very exciting to see how these findings fit into the bigger picture." Another author, Alice Booth, co-author of the paper, said, quote, "It is really exciting to finally detect these larger molecules in disks. For a while, we thought it might not be possible to observe them." Okay, so now they make a comment here about dimethyl ether. I don't know much about this chemical, but what do they say? It is an organic molecule commonly seen in star-forming clouds, but had never before been found in a planet-forming disk. Okay, so I should have clarified that earlier. Earlier I was talking about clouds in space, and I kind of grouped everything together. Apparently this chemical has been found in star-forming clouds, but not in a planet-forming disk. And that's an important distinction to make. The researchers also made a tentative detection of methyl formate, a complex molecule similar to dimethyl ether that is also a building block for even larger organic molecules. Wow. Okay, so that's really impressive. The molecules were found in the planet-forming disk around the young star IRS-48, the constellation Ophiuchus. It's been the subject of numerous studies because its disk contains an asymmetric cashew nut-shaped dust trap. Fascinating. So this region likely formed as a result of a newly born planet or small companion star. It's causing some gravitational effects. None of this has to do too much with biology, but it's interesting nonetheless. Okay, here they get back into the biochemistry of it all. Quote, many complex organic molecules, such as dimethyl ether, are thought to arise in star-forming clouds, even before the stars themselves are born. In these cold environments, atoms and simple molecules like carbon monoxide stick to dust grains, forming an ice layer and undergoing chemical reactions, which can result in more complex molecules. Okay, so that's super cool. So in the study of like the origin of life on Earth, one of the big hypotheses is that life may have originated in deep sea vents, or in some of these, in some environment where the biochemistry has a mineral substrate that it can work off of. And this is because that mineral substrate provides this chemical environment with the right pH and a surface that's kind of complex and has like features where chemicals can build up or aggregate and react, where water can be stored, and the mineral itself also provides binding sites for like catalytic activity that can facilitate some of these chemical reactions. And so it's really cool to see that same principle at work here in space, where they're talking about these dust grains that get covered in ice. And so you have this structure, this interface of mineral coated in ice. And so there's that interface of water and mineral, and organic chemistry can happen there. And that's really exciting. That's really cool. And if every single ice-coated dust grain is pretty much its own nucleus that's trying to ignite the spark of active biochemistry, if you're talking about a planet-forming disk, who knows how many countless trillions of dust particles coated in ice you're talking about. That's a lot of rolls of the dice, so to speak, if we're talking about the chances for some of these biochemical systems to develop and produce actually living systems. They also recently discovered that the dust trap in the IRS-48 system in the disk is it's also an ice reservoir harboring dust grains. Okay, there we go. I already read that part. Why is this important? So what makes this even more exciting, explains Booth, is that we now know these larger complex molecules are available to feed forming planets in the disk. This was not known before, as in most systems these molecules are hidden in the ice. So the article continues, the discovery of dimethyl ether suggests that many other complex molecules that are commonly detected in star-forming regions may also be lurking on icy structures in planet-forming disks. These molecules are the precursors of prebiotic molecules such as amino acids and sugars, which are some of the basic building blocks of life. By studying their formation and evolution, researchers can therefore gain a better understanding of how prebiotic molecules end up on planets, including our own. So they quote Ninken van der Merel, a lead in observatory research who also participated in the study. Ninka, I'm sorry if I'm mispronouncing your name, said, quote, we are incredibly pleased that we can now start to follow the entire journey of these complex molecules from the clouds that form stars to planet-forming disks and to comets. Hopefully, with more observations, we can get a step closer to understanding the origin of prebiotic molecules in our solar system. Unquote. All right, well, there you go. That's a really cool study. So there's a giant new organic chemical found in a planet-forming disk. And this is a chemical that is a building block for the building block. So it would facilitate the emergence of organic chemistry. And if life were to ever emerge in the star system, it's obviously unlikely, but were it ever to do so, these chemical building blocks would presumably be an integral part of that process. And in a larger sense, this is also a rather indirect way of searching for biosignatures. Like, say we're looking at a star system that's several thousand light years away, and we see that it's rich in biochemicals, like in clouds or maybe in a debris belt or something like that, like the asteroid belt. This could give us clues as to the overall chemical composition of the solar system as a whole, and this in turn could inform us as to whether, perhaps there's some rocky terrestrial planets that have enough carbon compounds available to sustain an ecosystem, a biosphere, life. Very exciting stuff. Okay, and here's the paper for it. published in Astronomy and Astrophysics, a major asymmetric ice trap and a planet-forming disk. I'm not going to go into the paper too much here. It's a lot of really intensive chemistry, and it kind of runs tangential to my kind of superficial alien interest in the topic. But I just thought it was a really interesting story. If you want to read the paper, it's available. It's available for free. The full paper is, so you don't need a subscription or anything like that. But yeah, really dig into this. A lot of technical stuff goes over my head. A lot of the chemistry stuff goes over my head. But yeah, check it out. See what you think. It's really interesting stuff. Okay, so that's our first science news story for the day. We got another one coming up. NASA starts building the Europa Clipper spacecraft to search for alien life on Europa. All right, so that's really, really cool. Okay, so this Europa Clipper mission is something I've been really excited for a while. So one of the most exciting missions that NASA has planned for the near future, there's a lot of missions are being planned for the near future, but the one that I think is one of the most exciting is this Europa Clipper mission. It's scheduled to launch in 2024, and it'll send a probe that's about the size of an SUV or like a Jeep out to Jupiter. It'll orbit Jupiter and get a closer look at its moon, Europa. Now, this moon is of extreme interest to astronomers and astrobiologists, and to me, because it has a massive, massive subsurface liquid water ocean. Europa is covered in kilometer-thick sheets of ice. But below the ice, there's a liquid water ocean. It's very salty as far as we can tell, but it's estimated to contain more than twice the amount of liquid water that exists here on Earth. Yeah, that's incredible. Okay, so let's dig into this SciTech Daily article and see what they have to say about it. Okay, when it's fully assembled, NASA's Europa Clipper will be as large as an SUV with solar arrays long enough to span a basketball court, all the better to help power the spacecraft during its journey to Jupiter's icy moon, Europa. And just about every detail of the spacecraft will have been handcrafted. Okay, so here they're talking about the assembly effort at the JPL in Southern California. The main body of the spacecraft is 10 feet tall propulsion module. It's got a 10-foot wide or a 3-meter wide high-gain antenna. All these cool features so we can send messages and get data back and stuff, even though it's going to be like way far out. Okay, this is where it gets really interesting. This is where they start talking about Europa and the biological aspect of this mission. Quote, Europa, which scientists are confident harbors an internal ocean with twice the amount of water in Earth's oceans combined, may currently have conditions suitable for supporting life. Europa Clipper will orbit Jupiter and conduct multiple close flybys of Europa to gather data on the moon's atmosphere, surface, and interior. Its sophisticated payload will investigate everything from the depth and salinity of the ocean, to the thickness of the ice crust, to the characteristics of potential plumes that may be venting subsurface water into space. And now, in past science news segments, I've talked about that. There have already been some studies sampling some of that water that's being vented into space. And those plumes are surprisingly rich in biochemicals, suggesting, potentially, that there's a hotbed of biochemical activity in the liquid water ocean under the Europa ice, which is just crazy awesome. Okay, so the first science instrument to be completed was delivered. Okay, so they're just talking about the process of building it. They need to be sure the instruments can communicate with the flight computer, the spacecraft software, and the power subsystem. Once they've all been integrated, then it's off to Cape Canaveral, Florida for an October 2024 launch. More about the mission. Missions such as Europa Clipper contribute to the field of astrobiology, the interdisciplinary research on the variables and conditions of distant worlds that could harbor life as we know it. And, personal side, it's one of the coolest biological disciplines in the world. Just stating facts. While Europa Clipper is not a life detection mission, it will conduct detailed reconnaissance of Europa and investigate whether the icy moon with its subsurface ocean has the capability to support life. Understanding Europa's habitability will help scientists better understand how life developed on Earth and the potential for finding life beyond our planet. Very cool stuff. Very, very cool stuff. I'm super excited for this. When we had that first flyby of Europa, and it came back with high resolution photos, and later missions were able to get samples of the plumes and stuff. Every single time, it's just boggled my mind how amazing and exciting it is. And you watch a movie like Europa Report, it's definitely more Hollywood than science fact, but man, that movie is just so awesome, and it really just primes your imagination about what could live under this icy shell, what could live in these pitch dark, high salinity oceans. Will we find, some kind of crazy fluorescent alien octopus like was seen at the end of Europa Report? Spoilers. Or is it just going to be, a population of microbes? Perhaps the entire ocean is, full of this rich microbial ecology, but there's no complex organisms like fish or krill or anything like that. That'd be kind of a bummer, relatively speaking, but it would still be really cool because you have this giant alien microbial ecology. And considering the nature of this potential ecology being encased in ice in this distant moon orbiting Jupiter, it's quite likely that this life represents its own unique biogenesis event. It is its own unique lineage, unrelated to the life on Earth. And that's super exciting because that has major implications for life elsewhere in the solar system. If we had two different lineages of life emerge in one solar system, that means that the odds for finding life, even if it's just microbial life, but the odds for finding life in other solar systems, if that's the case, goes up dramatically. And it would almost be unreasonable to the point of absurdity to insist on the theory that humans and life on Earth is the only life in the universe, or life in our solar system is the only life in the universe. But yeah, we're still speculating, but I can't wait until this Europa Clipper mission makes it out there to Jupiter and starts searching for signs of alien life or habitability on Europa. Very cool stuff. Okay, and now let's go to our final story for the day. This is a really cool one. So according to a NASA press release, we have passed an incredible milestone with respect to the search for alien worlds and worlds that might harbor alien life. So recently, there was an addition of 65 new entries to NASA's Exoplanet Archive. And with that new addition of those 65 new exoplanets, it brings the number of confirmed exoplanets past 5,000. Now, in the early 2000s, so about 20 years ago, there was just a few dozen confirmed exoplanets, barely more than 100. Our understanding of solar systems elsewhere in the galaxy was almost non-existent. We knew so little about them. But now we've cataloged over 5,000 confirmed exoplanets. And among all of these worlds, there is a breathtaking diversity of size, mineral composition, geochemistry, orbital period, temperature, atmospheric composition, atmospheric pressure, countless other variables. We've discovered exoplanets that meet our expectations. We've discovered exoplanets that have surprised us with one or more features of their orbit or their physical structure. Now, we'll get into it, but there's a paragraph in this press release that reads, quote, "The 5,000 plus planets found so far include small rocky worlds like Earth, gas giants many times larger than Jupiter, and hot Jupiters in scorchingly close orbits around their stars. There are super-Earths, which are possible rocky worlds bigger than our own, and mini-Neptunes, smaller versions of our system's Neptune. Add to the mix planets orbiting two stars at once and planets stubbornly orbiting the collapsed remnants of dead stars," unquote. So there's, going through a laundry list of all these different kinds of planets that they found. But let's get into it. Okay. The count of confirmed exoplanets just ticked past the 5,000 mark, representing a 30-year journey of discovery led by NASA space telescopes. Not so long ago, we lived in a universe with only a small number of known planets, all of them orbiting our sun. But a new raft of discoveries marks a scientific high point. More than 5,000 planets are now confirmed to exist beyond our solar system. Okay, here's that paragraph that I quoted. There's a couple videos that NASA included in here. These are really cool. So for most of human history, the only planets we've known were the small number orbiting our own sun. You can see Mercury and Earth and Venus there. But over the last 30 years, we've been discovering planets that orbit other stars. And so here, you saw all those little circles popping up on the map of the galaxy. Those are all new planets being discovered in like a time-lapse fashion. Everywhere we've looked, we found planets, and there are so many stars left to search. These 5,000 worlds include a tiny fraction of all the planets in our galaxy, which can number in the hundreds of billions. And then, so this video starts talking about future telescopes. So for example, the James Webb Space Telescope may be able to detect methane as a potential biosignature, and that'll be super exciting. Okay, so let's go on. What else do they say here? Jesse Christensen, science lead for the archive and a research scientist with the NASA Exoplanet Science Institute at Caltech in Pasadena, said, quote, "It's not just a number. Each one of them is a new world, a brand new planet. I get excited about every one because we don't know anything about them." Okay, so the article says, the steady drumbeat of discovery began in 1992 with strange new worlds orbiting an even stranger star. It was a type of neutron star known as a pulsar, a rapidly spinning stellar corpse that pulses with millisecond bursts of searing radiation. Measuring slight changes in the timing of the pulses allowed scientists to reveal planets in orbit around the pulsar. Finding just 3 planets around this spinning star essentially opened the floodgates, said Alexander Wolszczyn. I am sorry, I'm definitely mispronouncing your last name, who is the lead author of the paper that 30 years ago unveiled those first planets to be confirmed outside our solar system. If you can find planets around a neutron star, planets have to be basically everywhere, he said. The planet production process has to be very robust. Okay, so skim through the article a bit. He continues, to my thinking, it is inevitable that we'll find some kind of life somewhere, most likely of some primitive kind. So he also added, they're paraphrasing him, the close connection between the chemistry of life on Earth and chemistry found throughout the universe, as well as the detection of widespread organic molecules, suggests detection of life itself is only a matter of time. All right, so now this is another really cool video here. Basically, this is a map of the galaxy, and every little dot that you see pop up here over time is a new discovered exoplanet. So there you go. There was one. Oh, there's some right there. Oh, they start popping up more and more. And you can see through this time lapse, it's the year 1999. Now it's the year 2000. You can see this tracker up here at the top of the video. As time goes on and we invest more and more resources into scanning the skies, the rate of discovery picks up. Also, our methods are getting more sophisticated. We're getting better at it. And yeah, things really start to pick up here. I mean, look at all these discovered exoplanets. Yeah, it just doesn't stop. You have more observatories from around the world coming online, more groups focusing on certain areas. Like there's that one area there with all the planets that were discovered, that big purple mass. Other research groups are studying other parts of the sky, and so you have these clusters of planets being filled out in other places. But yeah, by the time you get to 2022, there's over 5,000 exoplanets. This is really incredible stuff. How to find other worlds. Okay, so this part of the article, they're talking about like the difficulties, the technical issues that we ran into when we were first trying to develop these methods to discover worlds, and we're still working on it. It's a work in progress. The article says, quote, "Finding small rocky worlds more like our own required the next big leap in exoplanet hunting technology, the transit method." And so that's when the star or the planet orbits in front of the star, and we can detect a dip in the light. It's a useful method, but it has its limitations. For example, if the rocky planet is really small and the star is relatively big and bright, that dip in light can be small enough that we may not even notice it. And furthermore, we're only able to detect planets this way if those planets orbit, if their orbit intersects the line between us and their star. Like, we'll only see it if the planet orbits in the way of the light of the star. If the angle of the orbit is anything else and it doesn't overlap, with our view of the star, we're not going to be able to detect it with the transit method. So there's some limitations, but it's been a really impressive, really useful method for the time being. And it'll continue to be useful into the future. But we're definitely going to have to develop more techniques to spy some of these much smaller planets that aren't so conveniently aligned for our viewing perspective. Now, in terms of the variety of the planets they've discovered, this is a really cool infographic here. So this is the chemical and structural variety of the planets, of the exoplanets that have been discovered so far. So 30% of them are gas giants, the size of Saturn or Jupiter, or they're many times bigger. And in some star systems, they orbit really close to the star, and so they're extremely hot. They say here they can be hotter than some stars. Like if you have a gas giant orbiting really close to a star, it's going to be superheated. And there's other stars out there, like dwarfs, for example, red dwarfs, brown dwarfs. They're very cool. And so, you could... they're pointing out here that we've found gas giants, basically, that are hotter than actual stars, which is just... I mean, that's a trip. That's mind-blowing. 31% are super-Earths. Planets in this size range, they range between Earth and Neptune. They don't exist in our solar system. Super-Earths, a reference to larger size, might be rocky worlds like Earth, while mini-Neptunes are likely shrouded in puffy atmospheres. So this is an interesting category of planets that we've seen exoplanets in this category elsewhere in the galaxy, but our solar system, as they say here, doesn't actually have this type of planet in it. These would be like rocky planets that are much larger than Earth, that might have really thick, dense atmospheres. And so they're going to be in between the size of like Earth and Neptune. They might not be habitable. The gravity might be too high. The atmospheric pressure might be too high. Depending on how far they orbit from the star, they might be too cold, even with a thick atmosphere full of greenhouse gases, like water vapor, for example, carbon dioxide. Still very interesting that 31% of exoplanets that we found are super-Earths, and there's no super-Earth in our solar system. That's an interesting incongruence, but there's an explanation for it. And it's mostly because these bigger planets, the super-Earths, the gas giants, the Neptune-like planets, they're all big, and so therefore they're easier for us to see. We can detect them easier with the transit method. We can detect them easier with the wobble method. The terrestrial planets are much harder to see, simply because they're so much smaller. So 35%, so this is the plurality of exoplanets, are Neptune-like. Similar in size to Neptune and Uranus, they can be ice giants or much warmer. Warm Neptunes are more rare. Interesting. And then last but not least, 4% of the discovered exoplanets are terrestrial. These are small rocky planets around the size of our home planet or a little smaller, so like Mars or maybe even Mercury. But the reason that only 4% of discovered exoplanets are terrestrial like this, the small rocky planets, is because they're small. They're hard to see. And as we develop more sophisticated telescopes, more powerful telescopes, we'll be able to find more of these terrestrial planets. And so I would expect this proportion of the total exoplanet count that was terrestrial to go up substantially. But that's going to take time. We might not see this percentage go up substantially for another decade or so. It depends on the results from the James Webb telescope, as well as any other telescopes or astronomy projects that are put forward in the next decade or two. But yeah, this is just a super cool milestone. Super cool stuff. Astronomer William Borucki came up with the idea of attaching extremely sensitive light detectors to a telescope and then launching it into space. The telescope would stare for years at a field of more than 170,000 stars, searching for tiny dips in starlight when a planet crossed a star's face. And the idea was realized in the Kepler Space Telescope. He was a principal investigator of the now retired Kepler mission, saying that its launch in 2009 opened a new window on the universe. He said, quote, "I get a real feeling of satisfaction and really of awe at what's out there. None of us expected this enormous variety of planetary systems and stars, and it's just amazing," unquote. Yeah, I agree with this. I agree with a lot of the quotes from Mr. Alexander Wolfsgesen. Again, apologies for the mispronunciation of your last name. But I agree. I'm super excited for stuff like the James Webb Space Telescope to come online and start making its official observations and do spectroscopic analyses and stuff. Because then we're going to start discovering so many more exoplanets, and we're going to be able to study their atmospheres, get our first peek into the atmosphere of some of these exoplanets. This is just such a huge leap forward, and so this discovering 5,000 confirmed exoplanets, it's such an amazing milestone. Guys, we're going to discover alien life so soon. It's almost certainly going to be microbes that we're going to infer their existence based on a biosignature that we detect, but I can feel it. Like, it's right around the corner. 5,000 exoplanets and counting. Our technologies are only getting better. Yeah, dude. I'd be willing to bet money that we're going to discover alien microbes or biosignatures suggesting the presence of alien microbes within the next 10 years. And I'm pretty confident that the James Webb is going to be the instrument that delivers that information to us. So awesome milestone. Super exciting stuff. This was a few stories of biology in space. Hope you thought this was fascinating. See you next time.